Okay, so we're up to example 3. We're going to do another chi-square test for independence. So this one says the study was conducted to determine if gender is related to the number of songs downloaded on iTunes per year. A random sample of 200 iTunes users were interviewed and their responses are recorded in the following table. So we were given a contingency table with the results of this survey of 200 people. And, not all tables are going to look exactly alike. So this one has totals for the rows and the columns. In the previous example that we did, they weren't there. So it just depends. If it makes it easier, because the totals aren't part of the observations, so if it makes it easier, you can kind of add your own grid lines if they're not there. Just like this, just so we could kind of differentiate where the observed values are versus the totals. I just don't want to cover the numbers. So now we could kind of differentiate where the actual observations are versus the column and the row totals. Sorry, there's like a lag with the pen. There we go. So this is what I mean. Here are the column totals, and these guys are the row totals. And then that adds up to the 200 people, right, that there were all together. So let me just go back to blue. So the question is, based on the sample data, can we conclude that gender is related to the number of songs downloaded on iTunes per year at alpha equals 5%? So in other words, is there a relationship between a person's gender and how many songs they download on iTunes per year? So the first step is that we have to formulate the hypotheses. And whenever we're doing a chi-square test for independence, like I said in the previous lectures, the null hypothesis is what we are assuming to be true, right? And in this case, it's that the two variables are independent. And then the alternative is going to be that the two variables or the two classifications are dependent. So the assumption is there's no relationship, and we're trying to prove that there is. So the first thing we're going to do is formulate the hypotheses. So let's do that right here in step 1. So we said that the null is going to be that the two variables are independent. So gender and number of songs downloaded per year on iTunes are independent. So this is the assumption. And then the alternative is that gender and number of songs downloaded per year on iTunes are dependent. And we're testing at an alpha level of 5% or 0.05. So that's the first step, right? To formulate our hypotheses. Now what we want to do is determine the model to test the hypotheses. So we said that whenever we're going to test that two classifications are related, we're going to be using a chi-square test or a chi-square, and we're going to look at the chi-square distribution, which is skewed to the right. And this chi-square distribution in this case has degrees of freedom equal to R minus 1 times C minus 1, right? So we take the number of rows minus 1 times the number of columns minus 1. That'll give us the degrees of freedom. So in this case, we have male and female, right? So we have 2 rows, so 2 minus 1 times the number of columns, which is 3, because we have 0 to 50, 51 to 100, 101 and higher, so we have 3 columns. So 2 minus 1 times 3 minus 1 is 2. So this distribution has 2 degrees of freedom. So now we have to calculate the test statistic. We'll label it on the curve, and then that'll let us get the p-value, right? I showed you how to do this in the calculator in the last lesson, so we're going to do this again. We're not going to use that formula that I did with the first example where we have to sum up all those square differences, right? This is going to be much easier if we do the calculator. So we have to enter this data, this contingency table, into a matrix, right? So we're going to enter data into a matrix. And then we'll do a chi-square test. So you can pause here and enter your data in this table into a matrix. If you want to watch me do it first because you don't remember how we did the last one, that's fine. But I'm going to do it now. So let's enter this contingency table into a matrix. So let me just share my calculator and I'll go through the steps again. So to get to the matrix, we press seconds and then matrix. You see the button highlighted in red. I usually just choose matrix A. We could always just keep editing matrix A. So arrow over to edit. I choose 1, which is matrix A. This is the matrix that we had from the previous problem that we did last time. We could just type right over it. We don't need to change the dimensions of the table because it's still a 2 by 3. So it's 2 rows times 3 columns. So we could just hit enter, enter. We're not changing the 2 by 3. And now we could just start entering the observations. So we had 40. When you hit enter, it automatically arrows to the right. So then that next cell was 50. The next cell was 30. The bottom one in the second row was 20. Then we had 50 again, and then 10. So this is what our contingency table looks like as a matrix. So once we enter our matrix into the calculator, we could do a chi-square test. So we press stat, arrow over to test, and it's option C. So chi-square test. So the observed is the matrix where we entered that contingency table. I did it in A. You could just always use A, and then you don't have to think about it. But let's say you don't have anything there. The way we pull up the matrix name is press second and then matrix again. And names should be highlighted and choose the name that you want it to, pop in there. So this is A because that's where I put my matrix. So I'm just going to hit enter on A and then it puts A there. Now, you could put any other matrix for the expected. So what's going to happen is those are the observed values that we entered into that matrix, but it needs to calculate the expected. Remember how we did that with that first example? I had you guys calculate E, the expected value for every single cell. The calculator is going to do that for you, and it's going to place them in another matrix. I usually just put B there. It doesn't matter which matrix is there as long as it's not A. So let's say there was nothing there for you right now. You don't have anything there. Let's just put B there. So second and then matrix, and then I'm going to choose B. So now it's going to put all the expected values in matrix B, and then it's going to calculate chi-square using the formula that I did with that first example in the last lecture. We don't have to do it by hand. Calculators and do it for us. So let's calculate. And there's my chi-square test statistic. Let's go 2 places. So it's about 9.03. And then it also gives the p-value. So the p-value is 0.0110. Because that 9 is going to round up to 10. So let's fill this in on our model. So the test statistic is 9.03. I want you to label it on the curve. So we start at 0, right? Because all these chi-square values are positive. So it's going to be to the right. So let's say our chi-square test statistic of 9.03 is right there. Now, chi-square distribution is skewed to the right always. So the p-value is always going to be the shaded area to the right of our test statistic. So the area to the right of our test statistic is in yellow here, the one that I just shaded. So this is the p-value. And the p-value that we got was 0.0110. And I also want you to write it on step 3. So the p-value is 0.0110. And we hope for a small p-value, right? Because remember when I introduced hypothesis testing to you in chapters 9 and 10, or I'm sorry, 10 and 11, we always say that the smaller the p-value, the more significant the results of the test are. So the more likely we are to reject the null hypothesis. And we want the p-value to be how small, right? What are we considering small? Well, less than alpha, right? Because my decision rule, so let's look at step 4. We only reject the null hypothesis if the p-value is less than alpha. So we hope for a small p-value. Well, how small is small? It has to be less than alpha. So we're using an alpha level of 5% in this case. So is our p-value 0.0110 less than alpha of 5%? Yes. So since the p-value is less than alpha, we reject the null hypothesis to go with the alternative. And the alternative is that the two classifications are dependent. So gender and the number of songs downloaded on iTunes per year are dependent. So we can conclude that the number of songs downloaded per year on iTunes and gender are related or dependent. So we conclude that there is a relationship between the two variables. And that concludes our chi-square test for independence.